All right. Greetings to everyone from your various corners of the world, from Vancouver, British Columbia, where it's early in the morning, and I'm very pleased to be here with all of you today. Big thanks for inviting me to speak at this workshop. I'm going to shift gears a bit from what the other speakers have been talking about to focus on some other kinds of archives of paleo-environment using geochemistry. And I'm also going to focus on the work that me and my collaborators are doing on exploring paleo-environment in sub-Saharan Africa and some of the different methods and ways that we can get at paleo-environment throughout the Holocene, and how we can perhaps tap into a new resource, or a resource that's been around for a long time, but looking at it at a new way to explore environmental change in this region of the world. So the focus of this talk is going to be on woody cover and reconstructions of woody cover and what that means and how we can get at this through diverse archives. So why does woody cover matter? It's this fundamental piece of ecosystems. On an ecological scale, it's absolutely critical for ecosystem function and health, as well as for the carbon cycle. On kind of a very basic scale, zooming away from talking about the particular kinds of plant communities in an environment, just looking at the structure of an ecosystem, which is what woody cover tells us, is a really simple and reliable way to define biomes in the past and in the present. And it's in fact one of the reasons why UNESCO uses woody cover to define biomes globally. And the UNESCO definition for woody cover across various biomes is going to come up a lot in this talk. So I'll go through that a little bit later. And if we're specifically focusing on Africa, which, as a lot of people have mentioned, is a largely understudied region of the world, which is a real shame for paleoecology because it has the longest record of interaction with humans. It's where we evolved. So woody cover in Africa is this really critical component of the environment and of the paleo environment. And it's really closely and intimately tied to both our past and our present. The shifting variation in woody cover in kind of savanna or open grasslands or woody grasslands, you know, looking at the continuum from forest to open grasslands, changes in woody cover is deeply tied to our evolution going back to the Pleistocene. And it also is strongly impacted by anthropogenic activities in the present. We know that a lot of the kinds of human activities that we engage in for modifying the landscape, things like shifting patterns of burning or managing livestock or producing croplands, all of these kinds of things strongly impact woody cover. And so it's this really important piece, this very basic piece that merits a lot of exploration in the past. So in terms of the various archives of woody cover that we can use around the world, but also specifically focusing in Africa, we have a couple of different sources. So we have terrestrial archives of woody cover, and these are things like the carbon isotopic composition of leaf waxes, which I'm going to talk about a bit. Things like paleosol carbonates, which precipitate in soils from organic matter, as well as CO2. Pollen, which has been covered quite a bit today already, in phytoliths. And there's a lot of pros and cons to these various kinds of archives of woody cover. So the pros are they are site specific, so you can actually get a reconstruction of that environment from a particular archaeological or fossil site or historic site, as has been mentioned by is an archive that's being tapped into by the speakers we just heard from, and a lot of incredible groups looking at pollen through time. They're diverse, and we have a fairly okay sense of the spatial and temporal extent of the proxy. So these are things that are big pluses of these various kinds of terrestrial archives. The cons are that they can be quite patchy. You might not always get good preservation of these different kinds of archives at various sites. So they might not always be present in all places where you might want to use them. It can also be difficult sometimes to study them in anthropogenic or archaeological landscapes because it's dependent, if you're looking at an archaeological site, on the kind of sedimentation and site formation that you have that will necessitate the preservation of these archives. Now, turning to looking at these archives of woody cover in fluvio-lacustrine systems, and these are largely leaf waxes again and pollen, there are also pros and cons associated with this. So the big a big advantage of this is that you get large landscape scale reconstructions of woody cover. It's this big zoomed out perspective across hundreds of thousands of kilometers in many cases of what the environment looked like. And they're generally quite well preserved, and they're also often continuous records. So we tend to have fairly good age models for these kinds of records, which is wonderful. And the cons, of course, is sometimes this perspective is too broad of a scale. So if we want to know the kinds of environments that people were actually living in and interacting with on their day-to-day lives, this large basinal scale reconstruction doesn't quite get at those particular kinds of points in the landscape that we might want to know more about. Sometimes the spatial extent is not very well known. So things like leaf waxes and pollen can be transported on wind, as well as water. So they might come from even farther outside of the catchment of these areas. Sometimes detangling these inputs can be a little bit challenging. So there's a lot of different things to consider when we're looking at these diverse archives. And this is a really important point, the pros and cons of these different kinds of archives for why we might want to look at other methods to explore woody cover in the past. So my work is based predominantly on stable isotope geochemistry and particularly the light isotopes. And this is really great for looking at woody cover because we're taking advantage of the fact that the carbon isotopic composition, so the number of heavy to the light isotopes in various kinds of materials, is really different between C3 plants, trees, shrubs, and forbs versus C4 plants, which are the tropical warm season grasses. So the average carbon isotopic composition of C3 plants is about -26 per mil versus -11.4 per mil in C4 plants. And these are from a large database of modern plant values that have been corrected to pre-industrial delta 13C values to account for the offset of the combustion of fossil fuels. So this is a big difference. And this allows us to quantitatively calculate how much woody cover, how many C3 plants were on the landscape versus C4 grasses in landscapes where that can be really clearly delineated, which is the tropical environment and many parts of sub-Saharan Africa. So before I get into the model that we're working on, I want to kind of go through some of these ways in which we've looked at woody cover in the past. And these again are largely focusing on the African continent, but this has also been applied in other parts of the tropics as well. And one of the main ways, the kind of big model that was published in 2011 by Terrestrial and colleagues in Nature looked at this relationship between the delta 13C value of soil organic matter. This is the material from which soil carbonates precipitate from. So we can do this nice calculation if we have carbonates to estimate what it would be in soil organic matter space when we're looking at the past. And there's a really nice relationship between the carbon isotopic composition of soil organic matter, as you see here on the y-axis, versus the fraction of woody cover of the environment from which it comes from, ranging from 1, which is a forest, all the way to 0, which is sort of an open grassland. And down here you see kind of a broader, a synthesis of the UNESCO definitions of these biomes on this continuum. And in kind of even more simplified terms, and we're talking about various kinds of plant forms, you basically have essentially, it's not quite perfectly a linear relationship as depicted in this graph, but it's a near linear relationship of decreasing C3 woody covered trees, shrubs, and bushes from forest down to grasslands. And then everything else that makes up the landscape, that kind of herbaceous cover, which is C4 grasses and C3 forbs and herbs, fill in kind of the rest of that space. So Serling came up with this equation that is really simple and easy to use, relating fraction woody cover to the sine squared of this essentially linear relationship of delta 13C of organic matter, which is very widely used. Now, scale is a big problem, obviously, because it's only integrating what is immediately around this area. So this is an issue. Now, using leaf waxes is a really nice other archive that we can use. And the leaf waxes are the waxy cuticle covering plants, which also record the carbon isotopic composition of that plant. And a recent study by Zhang et al. Found that leaf waxes found in soils actually correlate really well to organic matter. So we can also calculate what leaf waxes would be in soil organic matter space, and then plug this into the woody cover model. The problem is various kinds of leaf waxes perform differently relative to soil organic matter. So some things like C28 N-alkanoic acid has an R squared of 0.82, but C31 N-alkane does not perform very well. It's only about 0.52, so there's variation in how this works. And then another method that was put together by McGill and others in 2013 is to simply take the end member values. So what are the values, the average values for C3 plants versus C4 plants from modern plants of leaf waxes, and put them on the same scale as soil organic matter, and sort of estimate where it would be in soil organic matter space so we can plug it into the woody cover model. And this is a really good method, but it's important to note that this is more of an estimate of woody cover. This isn't a direct connection between leaf waxes and soil organic matter. So it's important to keep that in mind as well. So that being said, there's one other archive from archaeological sites that we can use, we can tap into to explore woody cover, which is the carbon isotopic composition of herbivore tooth enamel. And herbivores are excellent recorders of their environment through their diet because they capture the carbon isotopic signal of the plants they eat. And they have this consistent offset between the plants that they eat versus what's in their carbon isotopic composition of their tooth enamel. And this is in sub-Saharan Africa. This is particularly looking at APP taxa. So this is Artiodactyla. These are things like bovids, Perissodactyla, which are things like rhinos and zebras, and Proboscidea, which are elephants. So now this brings us to this new method for looking at African terrestrial woody cover from herbivore tooth enamel. And the benefit of doing this is that it opens up a whole new realm of archaeological sites where we can look at woody cover that might not have things like leaf waxes, paleosol carbonates, good preservation of pollen, and the like. So this is a forthcoming publication, and my other colleague, Scott Blumenthal from the University of Oregon, has really been leading this effort, but it's a large effort from a lot of people. And what we did is we took a database of the delta 13C values of tooth enamel from APP taxa all across Africa. It's about 1,700 values. And we looked at the delta 13C average of these communities, and there's a particular taxonomic way in which we calculated this, which I won't go into here, but it's not just an average of everything. We were sort of sensitive to taxonomy. From 33 protected areas all across Africa, and we compared this to woody cover product, which is a 1 kilometer resolution scale product used with MODIS and quick scatterometer data. So it does a really good job of capturing above ground woody biomass. And we find there's a strong linear relationship between the delta 13C average versus woody cover. So now I'm going to get through this as quickly as I possibly can. We wanted to apply this to archaeological sites and compare this to some of these other archives of woody cover from larger catchment areas. So how well can we resolve what people were doing or what the environment looked like at particular archaeological sites using this new model compared to fluvial lacustrine sites? And it's very difficult to find a lot of sites that have all of these criteria to apply this. We do this in 4 areas, looking at Wonderwork Cave in South Africa compared to the Orange River, Makwe Cave, and comparing that to the Zambezi River here, and then sites in Eastern Africa. And this is also a large data set of about 800 delta 13C enamel values from 29 data units across 17 sites. And I compare this with woody cover from leaf waxes using both the McGill and Zhang method. So here is what this looks like. So down on the bottom, we have the woody cover reconstruction from tooth enamel from archaeological sites. I have the UNESCO definition here on this side. Up here, we have fraction woody cover calculated from leaf waxes. The dots and the air are from the McGill method, and then the line down here is from the Zhang method. There's obviously some mismatches. We have fraction C4 grass, and then we have aridity, which is calculated from deuterium from leaf waxes. And we see some really interesting things. In particular, Wunderwerk Cave over the Holocene was fairly consistent, and these sites indicate that people were kind of occupying a wooded grassland to grassland continuum, which agrees broadly with the leaf waxes from the Orange River, which integrates a lot of the southern rainfall zone in southern Africa. In Zambia and Makwe rock sculpture, we see something quite similar, where we have people occupying spaces from a continuum of wooded grassland to grassland, again, across the last 6,000 years. And this data from the Zambezi River, again, a very large catchment area, actually indicates that it was a little bit more wooded than the places in which people were occupying, although there is some variation in that, but it's sort of on this continuum from a wooded grassland to grassland, which is not quite connected to aridity. In southern Kenya and northern Tanzania, again, we see representation of wooded grassland to grassland archaeological sites over the Holocene, whereas the leaf waxes from the Lake Victoria Basin indicate more of a wooded grassland to grassland, fairly consistent throughout most of the Holocene. Lots of grass was available, even though there were some large changes in aridity. And then into Turkana Basin in Kenya and southern Ethiopia, things look a little bit different, where again, people are sort of occupying spaces in this wooded grassland to grassland space, despite the fact that the Turkana Basin was actually quite woody throughout much of the early Holocene. And then following this kind of sharp increase in aridity about 4,000 years ago, we get an opening of the environment. But it's a bit different places where people were living compared to what the records are telling us from the lake. So just to kind of summarize all of this information, and this is the sort of the beginning of a lot more of this work that we're doing here. What this is kind of telling us is that these aridity, and first of all, the aridity and fluvio-lacustrine records are generally decoupled for a lot of these catchment areas, with the exception being the Lake Turkana Basin. Also, it's quite interesting to see that across a lot of different places on the African continent, that woody cover at archaeological sites indicate this human occupation of these grassland to wooded grassland areas, which is quite interesting. And it's difficult to sort of tease apart what is a human impact to this environment versus what is occupation of a particular kind of environment. But this is sort of letting us open up another level of archive where we might be able to explore with other proxies how much of this might be attributed to human activity through fire or burning or pastoralism or other sorts of metrics. So what this method allows us to do is to provide a blueprint for understanding how these human occupied environments vary from these regional trends, and where we might be able to start looking for more evidence of anthropogenic impacts. So with that, I just want to thank the two people who've been largely involved in generating this woody cover model right from the beginning, Scott Blumenthal and Jen Cotton at Cal State Northridge, and all the various funding institutions that have supported this work throughout the past number of years. And thank you all for listening.